Here we're looking at the interpretation of what is this wave function psi. Originally, Schrödinger thought about this as an extension of the particle itself, the charge of the particle, and you had this distribution. If you square psi, that looks Gaussian, as shown below in the graph. And the problem with this interpretation is that, as we saw above in the previous slide, this wave function disperses, so it gets wider over time, and in fact, depending on the interactions, can split apart. And so we don't see particles that suddenly become much wider and split apart in their distribution. So this is not how we view psi. The modern interpretation, which pretty much all interpretations of quantum mechanics agree on, comes from Max Born, and it came quite soon after, only really months after Schrödinger's work in 1926. The idea was that Born was influenced by Einstein, and we go back to waves that we know about, such as the electromagnetic wave, and we know that for electromagnetic waves, the fluctuating psi is the electric and magnetic field strength. So if we just concentrate on the, say, the electric field, we can write this propagating wave as E, the electric field, is the amplitude, which is E max. So that's sort of the constant in front. And then we have our traveling wave, e to the I kx minus omega t. Okay, and one result that you may have seen last semester in electromagnetism is the energy density associated with this electric field is U. So U is something like a total energy per volume, and this is equal to 1/2 epsilon naught, which is a constant, E squared, where, sorry for the multiple E's, but E is the electric field, E tot is an energy. Now, Einstein was thinking about the wave-particle duality and this concept of photons. So for a photon, and I'll put here that this is energy. That's electric field, just to make it clear. Electric field. So this energy of a photon is h nu. And we can think about then this energy density in terms of photons as adding up the total number of photon energies to get our total energy divided by V, right? So that's the same thing as E total over V, the volume. So we can relate those two. Now, the final step that we're going to do is then think about what the probability of finding a particle is and how that's related to a number density. So a number density is just the little n is the total number of particles divided by the volume, and we can then see that that is proportional to U. The difference is that in energy density, we're multiplying by the energy of the photons. Here we just have the number of them. So we'll write that's proportional to the energy density. Okay? And then the probability of finding a particle then is related to this number density. If you had more particles in a fixed volume, then you'd be more likely to find one of them. Whereas if in the same volume you only had a couple, you would have a lower probability of finding the photon or the particle. So we can also say that this is proportional to a probability per volume in that volume space. So in that sense, what was U? So U was proportional to E squared, which is the square of the wave function. And now we're saying that's proportional to P over V. So considering all of that, we can now say that a probability density, so I'll write this as the probability density, is